Hello, everybody. Welcome back to another wonderful biology class. I'm so glad you're here. Today, we're going to start a brand new unit on the cell. Today is going to be a two-part lecture. We're going to introduce both the unit and the first module of this unit. There'll be four. So what you can expect coming up is today's introduction, which will jump straight into the chemistry of biology, also known as biochemistry. Then we'll move into the second module, Module 7, which looks at cell structure and functions. Then we'll move into cellular energetics or cellular energy, namely photosynthesis and cellular respiration as part of Module 8. And then we will wrap up with Module 9, which deals with cellular reproduction and sexual reproduction. All interesting things. I hope you're excited. It's going to be a good journey. I can't wait to walk it with you. So this unit's big, broad focus question is, how do plant cells function to keep a plant alive? And that's a fair question. And this obviously is not an actual plant cell. It's just an illustration of what an AI thinks a plant cell looks like. But you could have a large central vacuole, which is filled with water. You could have a nucleus. You have a cell wall around the outside that'll have a cell membrane around the edges. You could have some mitochondria and chloroplasts. We'll look into some actual diagrams of real cells in our exercises, in our works. I'm not using them for these lectures because I want to post these lectures online and let them be available for everybody. And so, as to not deal with copyright issues, I'm using AI to generate my images. And so you'll have to work with my explanations and then what we have in class. And between the two, I think you'll have a really good idea of what you need to know. So that's the question. And with that in mind, we're going to jump straight into the first chapter dealing with biochemistry. And the first lesson will deal with what is matter. Matter. Hopefully that's a word that you have heard somewhere before. And I have this picture of some molecules and some symbols, a B for boron, which is ironic because you would never find boron anywhere, even remotely near life at all. It's a metal and not a common one in organic systems. So matter, that's what we're looking at. And as we focus on the topic of matter, the question is, what makes up everything around us? It's a good question. What makes up everything around us? And in that question is going to be things about life and things about not life. So vocabulary for today include atom, nucleus, proton, neutron, electron, element, isotope, compound, ionic bond, covalent bond, and molecule. So a lot of vocabulary today, which is why I'm splitting this lecture into two halves. And let's get into it. Review vocabulary for today should be substance. And this, generally speaking, can also be interchanged with the term pure substance or substance. And this is the form of matter, or is a form of matter that has a uniform and unchanging composition. So whatever it's made of, it's all the same all the way through, and that would be a substance. Again, oftentimes interchangeable with the term pure substance. So matter, hopefully you know this, is anything that has mass and occupies space. So you can think of it as basically everything you can touch, see, smell, taste, hear. Well, hear is energy. That's the vibration of matter. So most of your senses deal with your interaction with matter. And about the only place that you don't find some kind of matter is the vacuum of space. And really, even in the vacuum of space, you have a very small amount of matter floating around. And matter is made up of, well, fundamental particles, but this book starts with atoms. Okay, and an atom is a nucleus with protons and neutrons in the middle and electrons swirling around the outside. Again, this is not a scientific model of an atom. but it's a nice artistic rendering. And it's good enough to kind of get our minds going. I will say that this textbook, or this text that we're using, doesn't talk about quarks and leptons and the Higgs boson particle or the fundamental field forces. And that's a little bit sad. If you take a higher level chemistry with me, we'll get to talk about all the things that make up atoms and even some things that should exist in nature, like antimatter, that we don't see enough of in nature, which is very odd and interesting. But for the purposes of this book and this class, an atom is going to be the smallest unit of anything that we're really going to talk about, even though you should know there are smaller things that do actually exist. Now, so looking at the structure of an atom, there are three main parts, or I guess there are two main parts. There's the nucleus, and then there's electron orbitals outside of the nucleus. And the nucleus is what's in the middle, and it is composed of either protons or neutrons. Okay, protons have a positive charge, and that just means that they have an attraction to negative things. Neutrons, they have the same mass as protons, which is one atomic unit, but they have no charge. You might almost think of neutrons as having a proton and an electron, which has a negative charge, in the same little unit of space, though that's not entirely the full story. But because they're neutral, you can kind of think of that way, and that might help you remember the difference. Protons are positive, neutrons are neutral. And if we ever talked about radioactive decay, we would talk about neutrons being converted to protons by emitting electrons, which is why I said thinking of them as having both a proton and a neutron in the same thing kind of helps a little bit, because then you can remember that it spits out an electron to become a proton during, I believe, beta decay, if memory serves me correct. Again, this is not part of this textbook. This is when I teach chemistry, so I would double check, have to go back and double check to make sure that that's correct. Now, electrons, as I already mentioned, have a negative charge. And what makes them really different than protons and neutrons is they have almost no mass. They do have a mass. It's 0.000000, could be missing some zeros, and then a 1 atomic mass unit. It's a very small mass, but they have almost no mass compared to a proton or a neutron. And that enables them to move at very fast speeds in orbitals, which are just paths, or some are spherical and some are dumbbell shaped and some have just inexplicable shapes, but it's patterns that they move around an atom. And so these electrons oftentimes will determine the chemical reactivity or the chemical properties of an atom, chemical and physical properties. And they tend to balance out with the number of protons, right? And we'll talk about that a little bit more here in a second. Now, an element is determined by the number of protons, which is why I said that protons and electrons have a strong relationship to one another. Because a proton has a positive charge and an electron has a negative charge. Each different element, which has a different number of protons, will tend to attract, by default, the same number of electrons that it has protons. There's more to it than that in terms of chemical reactivity, but just defining what an element is, this is a good way to look at it. So if I have an element of hydrogen, I have a single hydrogen atom, it has one proton and one electron, right? If I have helium, which is an atomic number of 2, meaning that it has 2 protons, well, then it has 2 electrons in its neutral state. Now, it's important to note that there are about 92 naturally occurring elements. I believe we're up to 117 meaning that we've created a few non-naturally occurring elements that decay, they break down because they're unstable rather rapidly after formation. But we can find in the Earth or the Earth's crust usually somewhere around 90 to 92 elements without too much effort. And that brings us to the idea of the periodic table. This diagram is not the actual periodic table. This is just, again, an AI's rendering of the periodic table and is a masterclass in why you shouldn't trust AI to get your information from, because it's like a 3-year-old child who can make it look like what you're looking for, but doesn't actually know the difference, right? So a periodic table arranges elements by the number of protons and then also groups them in columns, right, that match the number of number of electrons in their outermost shell, except for the transitional metals and intertransitional metals in the middle and in the bottom. And if you take chemistry with me, we'll go into that in a lot more detail. But for now, just understanding that the atomic number, the big number in the upper left-hand corner of each little box, tells you how many protons there are, and it's arranged from 1 to 2, 3, 4, 5, 6, 7, 8, and so on and so forth, is how this is organized. That will help you be able to find elements and look at them. And again, generally speaking, the number of electrons matches the atomic number of your element. Now, an isotope is something that you should have been guessing at already, because the question is, well, what about neutrons? What do those do? Why did we even mention those? If the element is determined by the number of protons, then what the heck is the neutron doing? And that's a great question. Hopefully you were asking it in the back of your head. Well, an isotope is the same number of protons, we'll say 2 protons here, and they're real close together, and different numbers of neutrons. So this atom of helium here, we'll call it, and again, this is an artistic rendering, not a real thing, has 2 protons and 2 neutrons and 2 electrons, we'll say. We'll just ignore this one right there. So this is helium, because helium has 2 protons. And because it has 2 neutrons, this is helium-2. Okay, well, in nature, you might have helium with just 2 protons, helium with 1 neutron and 2 protons, helium with 2 neutrons and 2 protons, or helium with maybe 4 neutrons and 2 protons. Okay, and each one of those with a different number of neutrons is called isotopes. Those are isotopes. For hydrogen, there's 3 isotopes. There's hydrogen 1, which is just hydrogen, hydrogen 2, which is hydrogen and a neutron called deuterium, and hydrogen 3, which I believe is 1 proton and 2 neutrons, and it's called tritium. And so you have 3 different isotopes of hydrogen. And the mass underneath an element, it's called the weighted atomic mass average, or the atomic mass, is a weighted average of the percent of each isotope, its mass, and its naturally occurring abundance averaged together. So again, in chemistry, we will walk through that in tremendous detail. For this class, just knowing that different numbers of neutrons makes it a different isotope, not a different element. Now, a radioactive isotope is an isotope whose ratio of protons to neutrons is unfavorable. And you might ask yourself, well, why should that be the case? Well, if you think about it, let's say that we have 3 protons in the center of an atom, its nucleus. Well, it turns out that positively charged particles, protons, repel each other. They push against each other. They exert force, right? In the same way that they attract electrons, there's something called the electromagnetic force that causes like charges to repel and opposite charges to attract. So while the negative charge of the electron is attracted to the proton, two protons will push against each other. And so what neutrons do, the role that they play in a nucleus, is balancing the repulsive force of your protons. Okay, and so if you have just 3 protons in a nucleus, that nucleus might be unstable because there's too much repulsive force and it causes it to fall apart. It causes some kind of what's known as radioactive decay. And that can be alpha decay, which is emitting 2 protons and 2 neutrons. It can be beta decay, which is emitting electrons and converting a neutron to a proton by emitting an electron. Or it can be gamma decay, which emits a really high energy radio wave, electromagnetic wave called gamma radiation. Very destructive, very powerful type of radiation that can cause serious illness if you're exposed to it at any high level. But the idea is that neutrons play a stabilizing role within an atom's nucleus. And so in nature, you find both stable and unstable isotopes. All right, that's all that I'm going to lecture on for this half of the lecture. Hopefully you learned a little something and it was useful to you. Thank you so much for listening, and I'll see you in the next one.